Participants, our expert have already joined. So after 3-4 minutes, we'll proceed.
So Mohan, Keshav, this is a view is okay, or should I go to full mode?
Sir, it's okay, sir. Sir, as
I can go to full mode. But Keshav, then let me know if a question comes up, okay?
sure, sir, sure.
अटेंडेंस के लिए टेस्ट करना है किसमें
The expert of current session is Professor Ravi Pandey, sir. Is professor and chair of physics at Michigan Technological University, Horton, USA. He received his BS MS from Harishankar Gaur University at Sagar and did PhD from the University of Manitoba, Canada. Uh, he participated in multidisciplinary efforts, theoretical and experimental, to build the programs in novel nanostructures and applications of semiconductors as the next generation optoelectronic materials with the industrial and national laboratories, and is the author of more than 300 plus publications. He is a fellow of American Physical Society since 2015. Uh, he has also organized and co-organized and participated in several conferences in the area of materials physics and nanoscale science. And he's we met with him during 2013, and since to till he's guiding to us, including our my guides are Dr. Mohan L. Verma and me and many researchers who joined and worked in our lab. So I request to Pandey sir to please proceed for his talk. Sir, please.
Thank you, Keshav. It's always good to be back. Shankaracharya, not in person, but via Zoom. And as you know, is Dr. Raghuvanshi, Dr. Verma, and you basically carrying the simulation part of material science in India. And it's good to see that Atul Yojana came to Shankaracharya, and I can share some of my research results with the faculty members from India. So again, let me again thank you, Dr. Raghuvanshi. You really twisted my arm to give a very early morning talk. It's 8 a.m. here, but I can do it for Dr. Raghuvanshi. And Dr. Raghuvanshi, you owe me a good chai and pan. So let's start. What I'm going to do is I'll shift the gear. The conference is about optoelectronics and devices, but I'll give you a glimpse of we call low dimensional materials, and provide you some of the properties which can be used for these either optical or electronic devices with applications in our mind. So as Dr. Rao said, I come from the Sagar, Madhya Pradesh. I did masters from there, and then spent some time in NPL Delhi, and then went to Manitoba to do my PhD. Spent some time in England also. So I do have a background in experimental characterization techniques, mainly spectroscopy and Limson materials. But later I switched to the modeling of materials, employing especially what we call is a first principles method. So my group has been really working in different areas. Is what we call is a cluster or periodic approach with the Hartree-Fock or density functional theory Hamiltonian. I started work with the crystals and then moved to clusters, nanostructures, 2D materials. And currently I'm really engaged in what you call is a nanobio world. How does biomolecules interact with these nanomaterials? Overall is the physics and chemistry of materials, but from a simulation or theoretical point of view. So I give a little background about these nanomaterials or low dimensional materials, then switch to graphene, talk about beyond graphene. And since it's a theoretical talk, I'll show you some of the equations and look into both electronic and non-linear optical properties, and then provide a summary of the talk. So as Dr. Raghuvanshi, Dr. Verma, and Dr. Rao know, I like to be engaged with the participants. So please do not hesitate. Whenever you have questions, just ask questions, and Dr. Rao or Dr. Raghuvanshi can let me know. I cannot see the screen. Question coming up. So please do not hesitate. कुछ भी हो, कैसा भी हो, जरूर पूछिए. तभी मजा आता है in a sense giving a talk to participants. So the theme of the whole workshop is optoelectronics, advanced materials and devices. So what in essence what we are looking at it is this so-called quantum mechanical effects of light on materials. And basically we talk about electronic materials, which tend to be mostly semiconductors, because that's what we use them in devices. So these so-called photonic materials or devices can have, you can see the applications in photovoltaics, which is the solar cells. We have photoconductivity, which we can be exploited in charge-coupled device imaging sensors. Then have stimulated emission, which is sort of laser diodes, and radiative recombination, which we see currently in LEDs. So you can see really is a direct application of these quantum mechanical effects to day-to-day sort of life in application areas. So it's very, very important timely workshop again, thanks to Dr. Raghuvanshi to organizing and sort of giving some glimpse of this area. So, as I said, I come from a materials simulation theory point of view. So in about 45 minutes, hopefully I can convince you that a fundamental understanding and a theoretical foundation of these interactions and either electronic or optical response of materials is really essential for looking into energy or health related applications of these materials. So you must have heard today's Dr. Tiwari's talk, which I noticed from Raipur, and he's a well-known expert in device simulation. But there are two more talks coming up, which is again is going to provide you a little more in depth. How do we do this simulation? Dr. Verma on day 4 is talk about IT12 in solar cells and how does the simulation can provide looking into the solar photovoltaic effects. And Dr. Keshav Rao will talk day 5, taking the bulk solid basically and providing how can we calculate the optical properties of the material, which then can be used to these application areas. So these are two important talks if you really would like to get into materials theory or simulation. So this is, I call a little pretty pictures, which gives you an idea. Okay. About what exactly the length scale we are talking about. As you know, is if you look at the meter, sort of a human size, and if you go further down, we have a nanometer size, is the DNA basis, an atom, and which again is transistor, drug molecule, antibody. They all sort of comes in this area. There's another cartoon, as I call, is man-made world, which is on bottom, and then we have the natural world, and you can compare the size of head of a pin is a millimeter, the size of ant, and as you go down to right, you can see the DNA about nanometer, and we have the gold quantum dots coming out in that same region. So they are basically the compatible, and as we know, as we reduce the size, and then quantum mechanical effects really become important. So how do the nanomaterials come into the picture? And I think the credit goes to the experiments, and especially the significant advances in imaging techniques that have occurred in the last 10 years. So what we could do is basically look into this so-called surface topography at atomic level. So we have mainly two tools. If we really want to look at 3D magnification, which really provides a high contrast, so we can look into the physical properties of the material specifically the structure and mechanical using atomic force or microscopy. But if you further go down to sort of 2D magnification using a scanning electron microscopy, it does provide a high depth of field, and then we can really look into the chemical composition of the material and so on. So this is again is one of the AFM image. You can see really a nanometer size gold clusters on a silica substrate sort of floating around in that sense. So that's a sort of a driving force, that advancement in these experimental techniques, which pushing the frontiers for these low dimensional materials for applications. Now, what is so unique about these materials? So this is again is a cartoon, which you can see if I look at the cube, centimeter by centimeter. So surface area of this cube is about 6 centimeters square. Now I further divide this cube into millimeter cubes. So what we have is the advantage, the surface area has gone about 10 times, about 60 centimeters square if we have the 1 millimeter cubes. But we jump from millimeter to nanometer and look at the enhancement in the surface area. So what is the key thing about these materials is the properties controlled by surface areas. And that's why they're being useful at that scale. So I provide this slide in terms of giving you sort of a classification of materials. As you know, in solid state, we have a metal, non-metals, or metal, semiconductor, and insulating materials, or insulating oxides. But here we use this quantum confinement to classify the materials in either 3D, 2D, 1D, or 0D. So the key thing is this confinement is again dictated by so-called electron hole pairs in one or more dimensions within the material. So if I choose this carriers to in all three directions, we call it a 3D. And as we start restricting the movement to two dimensions, we have quantum wells. One dimensions, we have quantum wires. And then we have a hardly confined in all directions. We have so-called quantum dots. So these are sort of a classification in this nano or low dimensional materials regime when we use a quantum confinement to it, sort of a definition. This is another view is coming out. So what we are looking at is basically in a given material, the number of electron states per unit volume, per unit energy, and we refer to density of states. So if you look at the energy distribution of carriers, really is from bulk going to sheet, wire, and you get the dot. You have sort of a continuous distribution. We have really a very, very localized distribution of these density of states. So quantum confinement really radically alters as we move from 3D to 0D in terms of the number of electron states available for transitions. So I call this is quantum mechanics 101. If we choose our particle size to be very, very small compared to the de Broglie wavelength of electron, so what we can have, you can see here is the discrete sort of energy levels, basically mimicking the Bohr's model. If you remember the Bohr's model, and you have hydrogen atom. So in this very small region, they have a sort of discrete energy levels. You can see the nice, well-defined transition. But as we know, we bring these atoms together, form a solid, which is, if you look at that Avogadro's number, then what happens is these discrete energy levels basically forms so-called energy bands. So the advantage what we have here is depending on the size of our particle, we can sort of manipulate the band gap, which again dictates either optical absorption or emission for a given material. So I again would like to show this slide to give you perspective is what kind of a length scale we are talking about. So we have on left hand side is the properties, and then right hand side is the given sort of nomenclature we define it. So for example, electronic transport, we talk about either Fermi wavelength or scattering length. And you can see is a 1/10 of a nanometer, or about 10 to 100 nanometers. We talk about thermal transport. So we relate it to so-called phonon mean free path, which is about room temperature is about 100 nanometers. We talk about the optical interactions, which again is optoelectronic materials important. We're talking about the wavelength in the medium, which is again about 100 to 300 nanometers. And finally, we have a magnetic interactions where we have short range, so-called exchange interaction, coming with again is a few tens of nanometers. But we do have a long range, so-called magnetic dipole-dipole interaction, which again tend to go up to micron. So what again is, why do we do the modeling aspect of the materials research related to experiment is we got to have a motivation. And our motivation is we definitely would like to provide the results of accuracy and reliability that we can, with a confidence, talk about or predict the physical and chemical properties of materials. That's a key thing. So this capacity is what I call is desirable on two grounds. First thing is, of course, whenever we pick up a model, we have to make sure that it is valid. So we had to take what were the available experimental results and compare the predictions and verify that we can definitely reproduce accurately the properties. And once we have the confidence in our model, then we can go on and either resolve processes which are accessible to experiment or basically very, very cannot be done using experimentally. So that's why we sort of gain this predictive capacity coming out of these model based on first principle methods. So we have a lot of tools available in our disposal, and you can see here, this is the time and this is the distance axis. At the meter level or the years, we have so-called the construction, engineering design, unit process design, process simulation. And as you move towards left, we can see we arrive at the nanometer regime in sort of a pico or femtosecond, so-called the quantum mechanical models, or we could go to so-called molecular mechanics model. So our group basically has expertise in this area. So the question comes in first, and this is I call is the solid state physics 101. If you go back to Bloch theorem, so the question anybody asks is how is it possible to compute the electronic structure of a solid that contain an infinite number of atoms? And simply we take advantage of, we exploit the periodic symmetry of the crystalline solid. And once you use a mathematical sort of transformation, what you can do is, again, this is basis is a Bloch theorem, which provides the velocity, and we take advantage of transmission symmetry, and we reduce a sort of infinite number of what called matrices to finite one, in so-called the K space, which is we have the reciprocal space, and this sort of makes our life much easier, and the calculations are doable in the present conditions. So the key thing is we really exploit the translation symmetry for solution of the problem. So this is again is just to give you about an idea. If I pick up a SiO2 alpha quartz with a given unit cell parameter, so easily one can define based on the real space, the so-called the reciprocal space, and you have these K1, K2, K3 different directions, and you pick up a so-called these the spatial K points. So these are the high symmetry points in a given material, and use these high symmetry points, and if you see the x-axis versus energy, to see the dispersion in these bands or in these eigen states be coming out. And as we know, is SiO2 is a sort of a insulating material, so it has a so-called occupied bands coming from 2s oxygen, 3p silicon, 2p oxygen, and we refer to them valence band. And then we have so-called the unoccupied bands or states. We refer to them conduction band, and the gap between conduction and valence gives us the band gap of a given material. And for insulating material, as we know, the Fermi energy is defined by the top of the valence band. So the key thing is how to construct the brilliant zone, and especially find out about the spatial K points, so that we can see the energy versus and dispersion of energy levels in a given material. So what we have is as a basis is the crystal we define in a sort of a unit cell, and applying the periodic boundary conditions. And then we have to define the so-called electronic structure at the atomic level. So suppose we pick up a SiO2, so we had to have a so-called the basis set to define electronic structure of silicon and oxygen. And that's comes from at the quantum mechanical level. And once we have it, we sort of solve a so-called Schrodinger equation for a given psi or for a given density. And this well-known standard nowadays methods are a Hartree-Fock method, or we call it density function theory methods. So that's the sort of a key thing. And both Dr. Verma and Dr. Rao, I'm sure, is going to talk more about how to do these calculations, what exactly the equations need to be solved. So let's move to now sort of a graphene, and what we call is a carbon-based material. And being a chemistry 101, as you know, carbon has this ability to form different kinds of bond. And because carbon has about S2P2, and you can see is so-called sp3 bond formation, which gives rise to diamond or graphite, diamond crystal structure. And if you go to sp2, which remains the sort of in-plane hexagonal rings bonding, and gives rise to graphene, or these are layered of graphite. And then we have so-called the sp bonding, which sort of provides a linear arrangements of these carbon atoms when they form a single or a triple bond with each other. So these are a variety of structural configurations come out of this, the uniqueness of the carbon-carbon bonds and the way they arrange themselves. So if we use this quantum confinement classification, then we can see is the graphite can be called as a 3D. And then if you look at the graphene is our 2D material. Carbon nanotube becomes 1D because carriers move axially. And then we have a 0D quantum dot. Similar structure is a fullerenes or C60 material. So let's move to now graphene. And if you remember, is we have the small pencil, a graphite pencil type 2. And if we further zoom in at the tip of the pencil, as using optical microscope, so it's about 300 times magnification, you can see some sort of a shape and the structures. If you go further down, using electron microscope, we have really is about 90,000 times. You can see now the surface of this graphite. And you go further down using scanning tunneling microscope, you can see really the hexagon rings on this surface. So taking again this uniqueness of the carbon bond, sp2-like, and if you look at the graphene, and if we have the structural configuration, imagine is we have the triangular lattice, and these two interpenetrating triangular sublattice form our hexagonal lattice. So we have a unique type A or type B, the carbon atoms. From there is you have primitive unit cell, and you can form the reciprocal lattice. Now this is again is a 2D material. So what we have is you can see the reciprocal sort of a coordinates in the two direction, either G1 or G2 vectors. And from there, you can define the high symmetry K points and plot the dispersion of the states with respect to the K points. And you can see here uniqueness is if I show you, as if take the occupied level coming down and the unoccupied, we call conduction band. So for the high symmetry point gamma 0, 0, 0, you can see there is a gap, a well-defined gap in graphene. But if you further move to so-called the K points, what we see is this gap sort of closes between conduction and valence band. And that's why we call graphene to be a zero gap material. So this closing of the gap and the way sort of it shows up, it sort of gives a uniqueness in graphene. Let me show you here. So these are referred to as so-called Dirac cones. And what it does basically it provides a very, very high in-plane electron mobility in this material. And as you know, being a carbon-carbon bond is mechanically strong. So mechanically strong material with a high electron mobility definitely is going to be a candidate material for devices. So we'll go back and talk to you. But before, let me show you some of the cartoons to synthesize material. As we know, the Nobel Prize was given by a group in Manchester, UK, about mechanical cleavage. Simply you take the Scotch tape on graphite and peel it. But again, you have bottom-up approaches, especially coming from the chemical vapor deposition. We can definitely deposit a carbon atom by atom, form a graphene sheet. It's not easy to grow graphene sheet, and you can see still that both SEM and STM graphs the flakes again is in micron size, not big enough. Especially they have a lot of zigzag, the edges, and the defects are also there, which are really bright in STM photographs. But progress is being made. So how do we know we have a graphene, we have grown a graphene. So as you know, we have a Raman spectra, basically, which does give a signature piece describing the vibrational modes in a given material. And this definitely depends on what kind of bonding these atoms have. So this is simple, you shine the laser, and what you do, you look into the scattered sort of light. And from there, depending on what conditions you have, you can have either Stokes or anti-Stokes scattering or Rayleigh scattering. And from there, you definitely can find a unique signature of graphene coming around as 57 centimeter inverse in Raman, and then say, aha, I have a very good material, which indeed is graphene. So this is one of the common method being used to identify the structure information about the quality of the material. So let me quickly go to device physics I call 101, which is the field effect transistor. And what is required, as you know, for any FETs, you have a channel, you have source and drain, and a gate, and you have insulating oxide material to insulate the carriers going directly to the gate. And if you have current and voltage curve, by manipulating the gate voltage, you can modulate the current between source and drain. But so what it does, it does require the channel material which we would like to use should have a finite band gap. It has to be a semiconducting material. That's one of the key requirement to make devices, FET kind of devices. And as you know, graphene, we have a problem because it does have a band gap at the different symmetry points, but at certain symmetry points, it has a zero band gap material. So simply you cannot take a graphene flake as it is and use in devices. So we had to now figure it out, can we induce a band gap in graphene, which is not large enough, and it still can provide such a in-plane electron mobility. So that's a sort of in about 10 years ago was the Holy Grail. So question is how to induce a tunable gap. So what people have done, especially 2009, is they have taken a bilayer of graphene. And if you apply the electric field You can see the bottom atoms of carbon feels electric field, which is different from the upper atoms. So you have a dissimilarity in these electronic structure between lower and upper carbon monolayers or graphene monolayers. And what it does is it induces the gap in this material. And people have made the devices out of this bilayer configuration. So our ideas came out is can we look into the alternates without applying the electric field? And remember, this is a simulation model. So we are trying to guide experiment with what can be done. So when we ask the inducer tunable gap, so what we could do here, if you bring in the graphene and we make a different material, in this sense, in this case, a boron nitride monolayer, advantage what we have is they are more or less structurally similar. There's a hardly very small lattice mismatch, but as we know, graphene is zero gap, but boron nitride monolayer is a semiconductor or insulating material, especially the monolayer wise, about 4 eV gap. So expectation is by bringing these two systems together, they are going to induce a different electronic distribution in the graphene lattice, which sort of causes the opening of the gap. So we thought, okay, let's do some calculations. And you can see left, the first one is a graphene. And here is the special K points. So this is high symmetry gamma point, this is M point, and these are the K points. And you can see graphene, there's a gap here, but it closes around K points. I look at the boron nitride monolayer. And again, we are looking at the K, gamma, MK in the reciprocal space. And you can see there's a nice band gap all over the brilliant zone. If I bring in graphene boron nitride now, and you can see from naked eye, nothing has happened. But when we zoom in, what we can see is here, there is a small band gap opening at the K point, which again is coming out of the presence of the boron nitride monolayer. So the question you ask then is it true? So what we see here is first, let's look at what has happened. So on the left, we have is so-called the valence band charge density, which we can plot. And look at the boron nitride. As you know, boron nitride is a semi-ionic material because there is charge transfer from boron to nitrogen. And you have nicely well-defined the localized nitrogen sort of electronic orbitals or states or density compared to graphene, where you can see is a homogeneous distribution. So what is coming out is this in graphene boron nitride bilayer system, the gap opening definitely occurs because of the boron nitride, because it induces inhomogeneous charge distribution. That's a key thing in opening the band gap. This is good. We know now we have the result. We know the reason, but can we verify it? So what we have in our field, like you do in experimental physics, we also have experiments using our model. So the idea came in is if this is the bilayer, and what happens if we decrease the distance between the bilayers? Okay, so expectation is if this is due to inhomogeneous charge distribution, then as we decrease the interplanar separation, the band gap should open more and more. Let's see what happens. So in this case, you can see here, this is the change in the band gap of this bilayer system. And this I call is a strain. So this is the equilibrium configuration where we form the bilayer. And if we squeeze in the separation, say, so to about 10%, you can see this significant rise in the band gap. So indeed, this experiment has shown us, using computers again, the model, that this increase in homogeneity comes from this interplanar interaction, which opens up the band gap. And as any experiment, what you got to have, we call the reference case. And you can see in reference case, we have the boron nitride bilayer. And if we decrease the distance, more or less it remains the same. So after doing this thing, came out to the idea is the interface is going to be very, very important if you want to make or fabricate the devices based on graphene based structures. So I thought, okay, let's see. We can look into it. And this is again one of the work of the postdoc Rodrigo. I know Keshav Rodrigo is on and on, but he can see his results. Look at the electron transport. So as you know, given the device, we have a contacts, and then this is our channel material. So simply we're looking at a source and drain in this sense. So we take the gold to be contacts and graphene to be channel material. So this is again is a cartoon coming off this simple electron transport. So you can see here that's our device. It still is a diode because we are not applying the gate field. But if you look at this is a depiction of the energy levels. So this is the discrete energy level of a graphene, we call it channel material. And we have the semi-infinite contacts, gold on left and gold on right. And what you can see here in this way, as I increase the voltage between source and drain, I apply the voltage, a bias, then there is a movement of the levels. You can see these left contact and right contacts move opposite to each other. And then still the current is zero here still. But the moment they match sort of the energy levels from the left contact to our channel material, you can see there is going to be a jump in the current and the current flows. So that's sort of the simulation. You can see the way we do our simulation by looking at left contact, right contact, and the channel material and applying the bias to calculate the current. So if you do the results, and when first I saw the result came out from Rodrigo and Shaw Liang, I did not believe it, you know. You can see here that this is the voltage, this is the current, this is our device. For graphene, is a nice ohmic-like conduction. We increase the voltage, we increase the current. But you look at the boron nitride monolayer. This has a gap, this is semiconducting, but it's more or less behaves like a graphene. So the grad student, he has done really is another 3 months of work and came back, said, no, this is what he sees, that boron nitride monolayer behaves like graphene in this diode device. So the question is why? So we looked into the case is what has happened at the interface. And you can see this is the gold contact, this is a graphene, and there is a very, very strong overlap of the electron density. Makes sense because gold and carbon has formed a strong bond. But surprisingly, we also find the case with the gold with the boron atoms or boron nitride. You can see the strong overlap. So what has happened is this strong bonding at the interface, which provides additional conduction channels, which sort of gives us the similar ohmic-like conductivity for both the cases. So then question as you ask is, what happens if we induce a distance or larger distance between contact and monolayer? Can we reproduce the nature of graphene being zero gap material and boron nitride being semiconducting? So this is again an experiment. Let's do it. So what we have is we talk about this contact and monolayer separation. And you can see here the separation goes from 3.1 to 4.0 angstrom. And for the case of graphene, you can see is a large transmission. 3.4 comes down, but it's still at 4.0, you have a finite transmission. Let's see what happens with the boron nitride. And you can see here, indeed, as we increase the separation, we find that we have a finite conductance at 3.1, but at 4.0, we have a gap. There's a very, very small amount of the current flows at 4 angstrom. So both sort of comes down to the case, indeed, the contact channel material interface gives us this ohmic-like conduction for both cases. So earlier, what we had done previously, we have given the separation between contact and the monolayer. Now we see is, let's see what happens if we increase the thickness of our channel material. So on left, you can see is going from monolayer to bilayer to trilayer. And for the case of graphene, you can see monolayer in black is very high transmission. But as we increase the thickness, the transmission sort of goes down, but it still remains finite. Surprisingly, in the boron nitride case, as you go from monolayer to bilayer and trilayer, you can see for trilayer, indeed, we have a gap. There is hardly any transmission at a Fermi of boron nitride monolayer. So, in summary, we had to be very, very careful, especially the experimentalist who wants to fabricate devices based on these low dimensional materials. If thickness is small, or say these are called monolayers, then the intrinsic nature of the material does not matter because the interface takes over. That's a sort of a key takeaway coming from this work, that indeed for monolayer case, we had to worry about the interface effects. And then we asked one of our colleagues to do some experiments, and he does find for the boron nitride case, the monolayer and so-called the 7-layer boron nitride, there is definitely a big difference in the nature of the current versus voltage characteristics. So in recent years, we have again these graphene-based field effect transistors. You can see is coming out of this very small 2-inch wafer with a very nice characteristics cut off at 100 hertz and 240 nanometer gate length. So you have this source drain, sort of the terminals. Gate is coming from top. And then you have insulating dielectrics so that the carriers cannot leak out. And then this is our channel material graphene, and then again is a substrate is coming out. This is another cartoon is coming out, making sort of a photovoltaic cell based on graphene on semiconductor heterojunctions. Always remember here. So it's a typical cartoon. You have front metal and back metal contacts, semiconductor to insulate the carriers, SiO2, and then we have a graphene deposited on semiconductor silicon. So what you have advantages again is a hot carrier collection and multiple exciton generation is a possible. And I presume Dr. Verma will talk more about these characteristics in his talk on day 4. So let me take a break for a few seconds, and Keshav or Dr. Raghuvanshi, any questions, comments?
Participants willing to ask any kind of query? There is a kind appeal for participants. Would you like to raise any query?
Please ask questions. Otherwise, in person talk, I go out in the room and request them to ask, because either it's a very boring talk or simply you're not following anything. You know, as a teacher, we have to have engagement. And that's what we miss in Zoom talks. No comments?
Sir, Hemant willing to ask. Yes, Hemant, you can proceed.
Go ahead, Hemant. Can you ask questions?
He said that he is willing to ask about the presence of spin-up states and spin-down states that affects the band gap.
Yes. Good question, Hemant. So what we have is when you have the, as you know, SiO2 or graphene as such, they are not magnetic materials. But you have the magnetic materials, then we have called spin polarized bands. So you may have a band gap in spin up, but if you look at the spin down channel, is may have a different band gap or hardly any gap at all. So magnetic materials, looking into the spin up and spin down band structure becomes very, very important.
Naren raised his hand. Naren, please proceed. Naren. Naren Kumar, please proceed. Naren, you raised your hand. Otherwise, please follow the chat box. Any other participants willing to ask anything? Please proceed.
Okay.
No questions.
I'll proceed. So let me look into so-called now the predictive capabilities of these methods. So what we are looking at is if you look at the periodic table, you have the group 5. And then we basically looked into the phosphorine, carbon phosphide, and antimony. These are the monolayers of phosphorus. This is the hybrid compound, carbon and phosphorus. And this is the antimony. So we did predict sort of the stability and structure of these this elemental monolayer, and it was synthesized recently. But related to the theme of the workshop, if you look into the typical properties, you know, it has a sort of a band gap in a monolar case, and but as we go mono to tri-layer, we have the closing of the gap. So you can manipulate the nature of transition from semiconducting to metallic by varying the thickness of the material. And if you look at the optical absorbance, especially the optical properties, what we are looking at is the response of the material to a perturbation caused by this electronic part of the electromagnetic radiation, which I think is Dr. Ravi will cover in his day 5 talk about the spectrum. So I simply just give a brief sort of cartoon. So what we are looking at the perturbation coming into a sort of when the electric field due to these photons is 0. And once we light incident the photon, then we have the perturbation. And what we have is in terms of the linear property is the dipole moment, which you can express in the Taylor series. And similarly, we have the non-linear properties, called beta or gamma, which again you can express in terms of the Taylor series here. So what we have is the properties which are related to dipole moment, or the alpha, the polarizability of the material coming out of the reflectivity or energy loss function or XPS, which I think I saw from the text. Dr. Rao will cover it on day 5. But we also can look into is called the second order polarizabilities or third order polarizabilities, which sort of relates to a non-linear optical properties called second harmonic generation, third harmonic generation optical rectification, which were useful for fiber optics for communication. So just gives you an idea about one can calculate so-called the absorbance coming from the transmittance. And you can see that monolayer graphene and monolayer antimony, if you look at the spectrum, 1, 2, 3 V coming from IR are visible. As you increase the layer, the absorbance increases. But for the monolar case, we have about 3% or 2.3% absorbance. But if I look at the antimony, a monolayer, it has a much larger absorbance. So there is a possibility is it can be used, what we call is an optical limiting material for different devices. This is again another cartoon, or rather the result coming as absorbance with energy. You can see the graphene monolayer straight about 3% going from 1 to 3 eV, but antimony monolayer has this peak coming out about 1.25 EV with about 4% absorbance. So this can be used as a coating to protect devices or the so-called the weapons in mid-IR tunable lasers, because they are being a better absorber than graphene. So next 5 minutes, let me look into these non-linear optical properties. And I said earlier is we are looking at now is the beta or gamma polarizability. And this beta with respect to the frequency sort of relates to so-called electro-optic Pockle effects. And that beta to omega is our second harmonic generation. Similarly, gamma is either optical Kerr effect, or gamma 2W is our E-Fish-G experiments. So there is a one-to-one relationship between so-called these microscopic properties with macroscopic signatures for NLO applications. So what we found is recently, one of the students have done, if we used these so-called the graphene-based heterostructures, we have very enhanced the second harmonic generation values, and it all comes down to the interface. The stronger the interlayer coupling is going to have, you're going to have a very strong response of the second harmonic generation in these heterostructures. You can see this claims about the heterostructures we are looking at. It's a graphene sitting on boron nitride, and SCC, there is hardly any difference between graphene and boron nitride in terms of the structure parameters. So they sit on top of each other. This is AA, and this is called AB stack, slightly displaced. But we have also the so-called the phosphorine, and you can see is different structures, astrostructure for graphene phosphorine compared to graphene boron nitride. So you create these structures, look into the different properties, and then we have the so-called the beta values. And what you do here is the graphene, you can see is a centrosymmetric material. So the beta is a 0 here, but as boron nitride has a finite beta values, But once we form a heterostructures here, either A or AB, you can see the values have gone up related to the values of the pristine monolayers. Similarly, if you look at the phosphorine, we have graphene, phosphorine on its own. When heterostructure, they provide a higher SSG response. So if this is the true is, like earlier we said about electron transport, is what we can play around, this the distance between these bilayer system. If I change the interplanar distance, say about from 3.4, which is in blue, to 3.0, what you can see again is beta has gone up more. So it comes down to indeed is this electronic coupling between adjacent layer does sort of determine the enhancement in beta values for these systems. So again, you can have a sort of a cartoon is providing the graphene and the omega incident light, but SHG is going to be 0 because of the centrosymmetry of the case. But once you form the heterobilayer, you can have a really nice enhancement in SHG for both cases, either graphene boron nitride or graphene phosphorine, which is pretty high. So let me close the talk, and thanks to all the students, postdocs, and collaborating colleagues over the years. Without their help and their work, we would not have done really this amount of work and advanced activities in this modeling of materials. So I hope in the end, I did manage to convince you, as once you have the model, which can be sort of verified with the experimental results, then definitely we can go on and predict the properties with a high degree of confidence. Thank you.
The participants are, there is a kind of field to raise any kind of query. Participants, any participant willing to ask anything? Yes, Naren, please proceed.
Yes, I'm audible, sir, now?
Yes, please proceed.
Yes, good evening, sir. Actually, my question is
Hello,
related
Naren.
to... hello, sir.
Sir, he is that guy.
Yeah. Sir, my question is related to my research. Actually,
Where are you from, Naren? Can you tell us?
yes, sir, I'm from India, but presently I'm
Yeah, I know, but
presently I'm research assistant in UAE.
okay,
Yes, sir.
go ahead.
So my question is related to electric field. I mean, I applied electric field on carbon nanotube, and I doped the nitrogen atom in carbon nanotube and slightly increased the number of nitrogen.
Mm-hmm.
And actually, my motivation is to check the magnetic moment. So what I found when I increased the number of atom with the, when I applied electric field,
Mm-hmm.
at particular point of electric field, I found zero magnetic moment.
Mm-hmm.
Then I tried to increase the number of atom, nitrogen 1 to 2. The same I found zero magnetic moment at particular point of electric field. So I'm not
So,
sure that I'm
Narendra, what I
doing something.
suggest is first you do what we call spin polarized calculations. Okay?
Yeah. Yes, sir.
And then you turn off your electric field.
Okay.
Don't apply the electric field. So just find out a single nitrogen.
Okay.
Can it induce a magnetic symmetry? The spin up and spin down are different.
Okay.
Does it have a magnetic moment without any electric field?
Okay.
Okay. And you plot it and then let me know. Because what happens is you have to have I call the zero field magnetic moment in the system. Because when you apply electric field, is definitely is going to increase the magnetic moment, but if already is a zero magnetic moment, it cannot increase it.
Okay.
So the first question I would ask is what is the magnetic moment for the case of zero electric field?
In pristine carbon nanotube.
Yeah. And you had to do a spin
I think there is.
polarized calculations.
Okay, I will do it. I think I tried, but for pristine, I think no, there is no magnetic moment in pristine one.
No, not pristine. Not pristine. Is n-doped.
N-doped. Actually, I don't have the data right now, but
We can talk more, okay?
Yes, sir.
Send me an email.
Yes, sure, sir. I have one more question, sir.
Mhm.
Suppose I have a hydrogen, tungsten disulfide sheet, and I want use this sheet as a hydrogen storage.
Mhm.
This is just an example. So the size of sheet is 4 by 4.
Mhm.
So I want to dope, just sense two hydrogen atom.
Mhm.
Does the distance between these hydrogen is matter, or
Yes.
how much?
As you know, is if they are close to each other, they would rather form H2 rather than being absorbed.
What? Yes, yes.
So my suggestion is the two calculations. One calculation when they are very, very far apart,
Yes.
and one calculation when they are 1 angstrom away. And
One
see the
angstrom.
difference in 1 angstrom.
Okay.
And see the difference, 1 or 1.5, whatever the minimum you can find on the surface.
Okay.
So these gives you two extreme data points. Case is a weak interaction and the other is a strong interaction.
Yeah.
And then you couple with your single hydrogen atom absorption.
Okay, sir.
So my guess is your V case when hydrogen are far apart is going to be simply 2 times your single atom absorption.
Yeah.
But the strong interaction when they are close to each other is going to be slightly different.
Okay, sir. I will try.
Yeah.
Thank you, sir. Thank you very much.
These are the specific questions. Any general questions?
Yes, participants, please proceed.
Dr. Raghuvanshi, you don't have any grading of pass and satisfactory scheme. If you don't ask question, you don't get marks.
सर
So ठीक है.
सर आपका तो इतना अच्छा
नहीं पूछना चाहिए क्वेश्चंस पूछिए ना.
हाँ सर क्वेश्चंस का थोड़ा सा प्रॉब्लम है सर ड्यूरिंग द टोटल एफडीपी क्वेश्चंस राइज नहीं कर रहे हैं ये तो थोड़ा सा
नहीं वो तो डॉक्टर वर्मा को मालूम है ना. डॉक्टर राव को भी मालूम है कि हम लोग रूम में जाते थे सबसे फिर क्वेश्चन पूछते थे.
Yes, sir.
Sir, one more question raised by Hemant Kumar.
Sure.
कैंडिडेट के बगल में खड़ा होकर क्वेश्चन पूछवाना पड़ता है भाई करके.
One more question raised by Hemant. According to his theory,
So
in 2D,
Hemant, the question you are talking about now, the different angle and how you are going to affect the optical properties. So always remember is we are looking at the macroscopic picture. So the different angle to me is if you're doing experiment, because theoretically it's not possible. So an experiment, if you do it simply, you are either increasing or decreasing the light intensity of a given direction. And if it is a polarized material, which is graphene is not, then you may have a different signal, which are the perpendicular to parallel orientation dependent. So it depends on the material. But so when you say optical properties affecting, so is a dielectric constant, perpendicular to and parallel to axis, and so on. Is that okay?
Sir, one basic point I would like to know. Sir, in which situation van der Waals forces, as we know, van der Waals forces are weak forces, but in which situation van der Waals forces or bond analysis can be done in 2D materials, sir?
Yes.
By following any particular situation, this kind of analysis must be applied. Like I'm
I think
working
what we
on
can
to.
do is, analysis simply you take the total charge density. Okay, and you see the total charge density of the, say, in terms of graphene interacting with boron nitride monolayer or another graphene. So you can see really is this electronic clouds are touching or sort of approaching each other without too much of overlap. Because remember, van der Waals bonding depends on the flexibility of the electronic cloud, plausibility. So the charge density in a bilayer system is not going to overlap, but simply is going to touch each other. And which we have seen in a lot of other cases where we did a nanobio study.
Okay.
Just a simple charge density. Don't get into the Bader's charge or other analysis.
Okay. Participants, any further question?
Can I go by the room how much time we have?
Right now it's 9:41. Sorry, 7:41, sir.
Professor Dharmveer, I can see your name here. Dr. Kashyap, Ms. Tiwari, Shreya Tiwari. No questions.
Sir, everything was very clear in your lecture, so there are no doubt and no question. But that's what the question is not trying to. Two things will be there. As a student, we are not getting, so we have the question, or we are getting everything. So your presentation was so nice.
Well, as you know, Dr.
No,
Dharmveer is
answering
Sir, I have
students
a question.
not asking questions when they are bored. You know
Sir,
about
I
it.
have
no,
a
no, I
question.
want. Yeah, I asked the question for the student also. I asked the question for the participant also. But whatever explanation was so super, so I'm not able to ask a single question. That's the reason.
नहीं,
If
ठीक है ना,
anything, I
but
can mail you
आप
and
जानते हैं
details,
ना
like
कि हम लोगों
details
की
like that.
जिंदगी है वो तभी होती है जब एंगेजमेंट हो, तब मजा
Yes,
आता
sir.
है
Yes,
ना.
sir. Yes, sir. Yes, absolutely, sir. I'll mail you if anything, sir. I'll mail you and thank you, sir.
Yes. But बस good. I'm happy कि कुछ भी अगर आपने लिया है, that's great for me. Which I only can do it from far away. Otherwise, next time I'll
Yes,
do it.
sir.
And
Yes, sir.
again,
It's
I
our
is
pleasure to have.
suggesting. Yeah,
Yeah, it's our pleasure to have a speaker like you, sir. Thank you, sir.
sure. Thank you, Doctor. Good. So, Dr. Raghuvanshi, Dr. Verma, Dr. Rao, thank you very much. And hopefully we'll meet again soon.
Yes, sir.
Sir, one
Okay,
question.
there's a
One,
question. Yeah,
sir,
go
one question
ahead,
raised.
Dr. Ganguly.
Sir, my question was that we had been hearing that graphene would soon replace silicon, but it has been almost 10 years, sir. So, what is the current scenario, sir? Is graphene really going to replace at least in next 10 or 20 years? Oh,
Dr. Ganguly is, as you know, the process from our labs. You know, we do fundamental research, and the industry.
yes, sir.
There is a lag. So if you go back and look at the history of silicon industry, it took really 25 to 30 years to mature for it come from a lab to chips. So the graphene is coming up. The the biggest challenge with the graphene is the substrate size. Still, they cannot have more than few micron, the flakes.
Yes, sir. Yes, sir. Right, sir.
And that flake is also is not defect free, is a lot of defects. So what we are looking at is definitely in the next 10 years, hopefully, now the advancement in manufacturing technology will scale up and go to industrial scale. But as a flake, graphene has definitely, because of not the electronic property, but the mechanical property started being used in composites with polymers to make automobile components. So that part is coming up. Now is electronic part has to come up because we really need to have a defect-free large sample. So give graphene industry another 10 years, hopefully we'll see something different.
Yes, sir. Hopefully, sir. Thank you, sir. Thank you.
No, look at our thing is our parents, we didn't have a single phone, remember the phone, and now look at what happens in 50 years.
Yes, sir.
Every corner has a
You know,
phone.
20, sir, not just 20, 50, 20 years, we have seen a tremendous change, sir, in just 20
Exactly,
years.
yeah. So it's pretty good. I think there's another question from Ms. Tiwari. I saw some. Yeah, go ahead, Shreya.
Good evening, sir. I just want to
Hello.
know, like while considering the multi-layer of BN and graphene, we found that the amount of current decreases as the number of layer increases in the case
Yeah.
of the BN. But the electronegativity of nitrogen is far more as compared to carbon. But how is this
Yeah.
even possible? I mean, the electronegativity is much more for nitrogen, and it is not in that favor for the carbon atoms. So how
So
this kind of fluctuation
yeah,
is
Shreya.
happening?
So what we are looking at, what is your background, if I may know? Is a chemist or physicist?
Chemistry, sir.
Yeah, see, I guessed it. So what happens? You're looking at the molecular picture, and we are looking at solid state where we have a large number of atoms forming these monolayers. So what happens is this electronegativity difference you're talking about reflects in the gap between occupied and unoccupied molecular orbitals. Okay.
Yes,
So
sir.
if you have a larger electronegativity difference, you're going to have a larger band gap or eye gap. Okay. And for graphene being carbon again is you're going to have, in this case, in the monolayer, zero gap, and you have finite gap. And when you combine them together, then what happens is this electronegativity difference or difference in bonding. So this carbon is looking at boron, the other carbon is looking at nitrogen. So they are experiencing a dissimilar electronic structure. So they're going to behave a little different, which induces a small gap in graphene. So same, your electronegativity argument sort of reflects in the band gap, which induces graphene to have a small gap, or in terms of the current.
Got it, sir. Thank you, sir.
Yeah.
So one more question.
Yeah, hi. Dr. Manuel, go ahead.
Manuel, please proceed.
I think he asked the question. Let me see.
Sir, how can we characterize the interspacing between the graphene layer and boron nitride?
Yeah, so Dr. Manuel there are two ways. If you're an experimentalist, you can look into the Raman spectrum of a particular monolayer, top or bottom. So this, what I'm showing the Raman shift. So there is an equation which sort of relates to the shift to the thickness of the material. So you can say bilayer, monolayer, trilayer, and so on. Is a well-known equation. In terms of the model, simply what we do is we induce a distance between these layers in our unit cell. Does that answer your question? Good. So Dr. Verma, our trick is working.
Yes, sir. Our trick is working.
Any other questions, please? So I think I had to go now because my office starts. So the message is hopefully think about doing simulations, and hopefully within a year when Omicron goes away, I request Dr. Verma, Raghuvanshi, and Dr. Rao to organize a workshop, and we can see you face to face and teach you some lessons there. Okay. Thanks, Keshav.
Yes,
Thanks,
sir.
Thanks. On.
Thank you,
Thanks,
sir.
Dr.
Bye,
Ravi.
sir.
Take care.
Thank you, sir. Thanks a lot.
Thank you, sir.
Bye. Yeah.
Bye.
Thank you to all the participants.
Thank you.
Who managed your time and
Thank you,
join.
sir.
Thank you a lot, you all. And on tomorrow we will join again at 10 o'clock. So thank you and good night. Thank you all.
Thank you, sir.
Thank you, sir. Thanks for the wonderful session, sir. Thank you.
Thank you to Pandey sir. His expertise actually mesmerized to all of us. So if any kind of query you'll have, you can email to him, and the remaining participants also. He will respond soon. So any kind of. Okay, thank you all.